Hi everybody. This video is on section 10.7, the second shifting theorem. So what we're going to do is we're now going to determine how to apply the Laplace transform to the unit step function. Okay, and as we learned in the last section, since every piecewise function can be written as some sort of combination of unit step functions, this means that we're going to be able to take the Laplace transform of a piecewise function. Okay, so theorem. This theorem has a name. It's called second shifting theorem. Okay, so I want you to suppose that the Laplace transform of f of t is equal to capital F of s. Then the Laplace of the unit step function at a times f of t minus a is going to equal the following: e to the negative as f of s. Okay. By the way, this is just another way of writing e to the negative as times the Laplace of f of t. Okay. So again, what I wrote above is really the theorem, but I just want you guys to realize that f of s is L of f of t, right? So this is just another way to write it, okay? But this is the second shifting theorem. This is what it says. Okay, so I would like for us to prove this theorem, and then I will talk a little bit about what it means, okay? So, proof. So, what is UA of t times f of t minus a? This is actually equal to 0, right? Because UA of t is 0 if t is less than a. So if t is less than a. And it's equal to f of t minus a if t is greater than or equal to a, right? Because UA of t is either 0 times the function or 1 times the function. Okay, so now we're ready to take the Laplace. So by the definition, the Laplace of UA of t f of t minus a is equal to, so we know we have to integrate from 0 to infinity. And we know that the definition is just e to the negative st, and then I put that entire function in there, right? UA of t, f of t minus a, dt. So what is this equal to? Well, I'm going to break this up into two integrals, okay? Because from 0 to a, this means that we're going to use the integral up there, so it's going to be e to the negative st times 0 dt plus, and then we're going to integrate from a to infinity of e to the negative st f of t minus a dt. So all I'm really doing is I'm using this for the first integral and this for the second integral, okay? However, this guy is just 0, right? So I don't have to worry about that because the integral of 0 is 0. So we're going to focus our attention on that second integral, okay? What I'm going to do is I'm going to do a u substitution. So what's the u substitution going to be? I'm going to let u equal t minus a, which means that du is dt. And that also means that t is equal to u plus a. So if I do that change of variables, let me actually continue over here. What does my integral become? Well, if this guy is equal to t, right? If t is a and I plug it into here, then that means that u is 0. So my new integral is going from 0 to still going to infinity. And now I'm going to have e to the negative s times u plus a, and then f of u du. So what is this equal to? Well, I can break this up as follows, okay? I can write this as e to the negative as times e to the negative st f of t dt. There are two things I did here. One is I used the rule of exponents to split up this e term, but then I replaced my u's with t's. Why am I allowed to do that? Because the t's or the u's are just dummy variables, right? They're just placeholder because when you do the integral, you're plugging in numbers at the end anyway, right? So to say that another way, when you're doing a definite integral, the variable you choose doesn't actually matter, because it's not going to, you can change your t's for x's for whatever you want. Now, the e to the negative as is just a constant, so you can actually pull it out. And I'm going from 0 to infinity of e to the negative st f of t dt. Except now we recognize that as just the Laplace transform. So this guy right here is literally the definition of the Laplace transform of f of t. And so the answer to that is e to the negative as times the Laplace of f of t, or another way to write that is e to the negative as f of s. So that's the proof. So this theorem is really just remembering what it equals, right? So let me write down this theorem. So of course, or let me actually write something down, okay? So what we have here is that the Laplace of u a of t times f of t minus a is equal to e to the negative as f of s, right? Now, what is another way of writing this down? There is another way, okay? What if you consider it as a function of t instead? Okay. This just means, so you can notice that t is being shifted, okay? And so what this ends up being is e to the negative as Laplace of f of t plus a. Okay? This is just another way of rewriting it, okay? But the idea is that you're shifting over, right? The t minus a becomes a t, or the f of t becomes a t plus a, okay? This is just a statement. These are equivalent. So, of course, the theorem works in reverse. And what I mean by in reverse is that if the Laplace of A is equal to B, this is the same as the Laplace inverse of B is equal to A, right? So they're just inverses of each other. And so what would the inverse of the theorem say? So this implies that the Laplace inverse of e to the negative as f of s is equal to UA of t f of t minus a. Okay? So this would be how you would do it in reverse when you're taking the Laplace inverse. And again, remember that f of s is really just the Laplace of f of t. And this is just going to equal UA of t f of t minus a. Okay, so these mean the exact same thing, all right? So again, these are equivalent, but this is mainly what you have to remember are these things that I'm boxing here. These are equivalent. Okay? So there's a reason why we call this the shifting theorems. So let me do this on the next page here. So let's compare the two shifting theorems. I want you guys to see why we call these the shifting theorems. Remember, one of them was called the first shifting theorem, the other one's called the second one. So again, we are assuming that L of f of t, just for shorthand notation, is capital F of s. So again, what this means is that we're assuming that f of t gets mapped by L to capital F of s, right? So this is what we know, this is what we're assuming. And so the first shifting theorem says that if you applied the Laplace to e to the at f of t, that you end up shifting your output to the right. Okay? So let me actually go ahead and let me do one more thing, okay? So that's what we did, and I'll talk about this more in a second, but now this theorem that we just learned says that these two get mapped to one another. But you could almost see that this is the reverse of the theorem that we learned before, in a way, not quite exactly the same, but in a way. And so what's happening is I put the arrow the other way just to show which way the shift is going, okay? So let me also put a different color here, okay? So this is going to be, everything here is in the world of S, and now everything here is in the t world, right? So now what we're saying is that the Laplace, by multiplying the input by e to the at, the output gets shifted, okay? So let's write that down here for this guy. This is the first shifting theorem. This says the output of the Laplace transform is shifted to the right. That is what this says, okay? By multiplying the input by e to the at, the output gets shifted to the right. Now, what about this other one? So this other one's a little weird, but this is why I drew the arrow going the other way, because it's the Laplace inverse that gets shifted, right? So let's write that down for this one. This is saying the output of the Laplace inverse is shifted to the right. Okay, so again, this is the difference between the two theorems, and you got to be careful. It is easy to confuse them. we need to be very comfortable going both ways, okay? The idea is that the unit step function multiplied by a function shifts the, is going to turn into e to the something on the right. Okay, but if you multiply by e to the something on the left, that becomes a shift on the right. Okay? So, let me just kind of write one more thing here. So first, shifting theorem. L shifts output to the right. So this means that S becomes S minus A, right? And the second shifting theorem this is saying L inverse shifts the output to the right. This means that instead of t, it becomes t minus a. Okay, so again, one more thing I want to point out here about this theorem, because we are going to do some examples and I don't want you guys to be confused. So I just want to also point out that when you're using this theorem, if you're going to write that this equals e to the negative as f of s, which is fine, just understand that this a and that a need to match. Okay, so you're going to see that as we do some problems, I may have to manipulate some problems and so that you are able to get the same thing there. Okay? All right, so what I want to do is practice using the theorem first, and then we're going to practice actually solving some initial value problems. Okay, so we now practice using the theorems to apply L and L inverse. Okay. All right. So let's do an example. Find the Laplace of f for f of t equals 0 for that t minus 1 in that interval, and then 1 in this interval. Now, this may seem familiar to you. We've already done this example as far as rewriting it using unit step functions. So I'll just say in example from the last section, f of t is equal to, what we found was that it was equal to u1 of t times t minus 1 plus u2 of t times 2 minus t. Now we want to take the Laplace of this, but I want you to notice that we don't have a minus 2 here. We have instead 2 minus t. So we want to fix this guy right here. So here's how we're going to fix it to make the theorem easier. I'm actually going to pull out a minus sign. And you're going to see us playing with pulling out constants quite a lot. It's because, remember, the Laplace and Laplace inverse are linear transformations, so it distributes a lot easier over negative signs and constants. So this is why we would rather have the form match. We don't need a positive there. So again, we're good now, right? Because that and that match. And this and this match. Okay. So then what would the Laplace of f of t be? So what you're going to do is remember how the shifting theorem applies, right? You multiply by e to the negative as. In this case, a is 1, so I'm just going to write negative 1s, just so you understand how I use the shifting theorem. And then that's going to get multiplied by the Laplace of t. Why t? Because again, this is the shift, right? We went from t minus 1 to t, right? And what about here? This is going to become minus e to the negative 2s. And then we're going to do the Laplace of t again. So what is the Laplace of t? The Laplace of t is 1 over s squared if we look at our table. And so our answer becomes, since I'm going to get a 1 over s squared for both of these, I'm just going to write the answer like this. E to the negative s minus e to the negative 2s, okay? So this is our Laplace. Okay? Okay, that one was not too difficult, okay? But we're going to do a trickier one now. Find the Laplace of f if f of t is the following piecewise function. 1 for 0 or t between 0 and 2, and e to the negative t minus 2 for t bigger than or equal to 2. Okay, this one's definitely going to be trickier, and also we're going to need to do this from scratch. So remember, for our first guy, understand that for our first or our top function here, I have, let me call it f1 of t and f2 of t. So what is f1 of t, the top guy? Remember, we're starting off with 1, and then we're turning it off at 2. So I'm going to write it like this. Okay? And f2 of t is going to equal, remember we're turning it on at 2, so I'm going to write u2 of t, and then we're not turning it off ever. So this is what it looks like. And so you add these two together to give me the f, right? Because all I'm really doing is I wrote this guy, this is my f1, and this guy is my f2. So I just basically wrote f as the sum of those two functions, okay? So f is going to equal, we're going to write it this way, 1 plus u2 of t times what? Well, I have negative 1 there, so it's going to be e to the negative t minus 2, and then minus 1, right? This is what I have. Okay? Okay, so what is this going to become? Well, what I'm going to do is I'm going to rewrite it like this. So I'm going to put the negative 1 first. And I'm going to put it like this, okay? Now, this has the form we want, right? Because we have a 2 there and we have a 2 there, so they match, right? And it's being subtracted. However, this one does not have the correct form. So how am I going to fix it? Well, what I can do is instead of writing a negative 1, I need to write it as something minus 2. Something minus 2, right? So what would it be? It would be 1 minus 2. So can't I write it like this? There we go, right? So now this guy and that guy match. And again, this guy and that guy match. So we apply the second shifting theorem. So this says that f of s, in other words, the Laplace of this is going to equal what? So I'm going to do the Laplace of 1 plus, this is going to be e to the negative 2s, and then I'm going to do the Laplace of 1, and then plus e to the negative 2s again, and then it's going to be the Laplace of e to the negative t. So what is that going to equal? Well, the Laplace of 1 is 1 over s, right? So it's going to be 1 over s plus, and I notice they both have an e to the negative 2s, so let me factor out an e to the negative 2s. The Laplace of 1 is 1 over s plus, and what's the Laplace of e to the negative t? If you recall, that's going to be 1 over s plus 1 if we use our table to remind us. So this is our Laplace of the function. Okay, so it's not really that bad. We're just trying to find a way to rewrite it so that it looks like what we know. What I want to do now is let's practice finding the Laplace inverse. So we now practice using the inverse of the theorem. Okay, so for this example, we're going to find the Laplace inverse of 2 e to the negative s over s squared plus 4. Okay, so now I want you guys to remember what the second shifting theorem says, right? The second shifting theorem says, and I'm just going to write it down for our reference here, okay? It says that the Laplace inverse of e to the negative as times the Laplace of f of t is equal to ua of t times f of t minus a. In other words, if we can rewrite the first guy as e to the negative as times the Laplace of something, you're then just going to take the input, the t, and shift it to the right. In other words, replace t with t minus a. So that's all we have to do here. So here's how we do it, right? This is going to equal the Laplace inverse of, so I know I have an e to the negative s, so let me write it like that. So I have an e to the negative s, and then what I have left is 2 over s squared plus 4. Do we recognize 2 over s squared plus 4 as the Laplace of something? So yes, isn't that the Laplace of sine of 2t? Right? So isn't this equal to the Laplace inverse of e to the negative s times the Laplace of sine of 2t? Again, look at your formula sheet, right? So this is our guy. So that means if we want to apply the Laplace inverse to this, we need to use the second shifting theorem. So by the second shifting theorem, this means that f of t, right, the Laplace inverse of that guy, is equal to what? Well, look at the theorem. We have to replace it with the unit step function. What's a in this case? A is the number that's being multiplied by s, so we are shifting over by 1. So it's going to be u1 of t, and then you're going to replace t with t minus a, so this is just going to be sine of, you're going to replace t with t minus 1, so that's going to be 2t minus 2. Okay. Okay, so that one wasn't that bad. The next one, though, is going to be pretty tricky. So actually, before I do it, so let me just say that in this next example, we will need to apply both shifting theorems. Okay, so this is why we have to understand both of them, because actually, once you learn this theorem, a lot of problems are actually going to use both theorems. We're going to use them all the time. And in fact, as you guys know, from doing initial value problems this way, you're going to have to apply the Laplace and then the Laplace inverse to solve a problem. So you may actually have to use both theorems multiple times. All right, so let's go ahead and look at the example. I want us to find the Laplace inverse of s minus 4 e to the negative 3s over s squared minus 4s plus 5. Okay, so we realize that this is actually the same as asking us for the Laplace inverse of e to the negative 3s times, and then s minus 4 over s squared minus 4s plus 5, right? So what I need to do is I need to write this guy right here. I need to write it as the Laplace of something. Or another way to think about this is you need to figure out what the Laplace inverse of that guy is. Okay, so let's see what we get here. S minus 4 over s squared minus 4s plus 5. Let's play with this a little bit. This is equal to s minus 4 over, remember the completing the square trick. If I write the bottom as s minus 2 squared, and then that would give me a plus 4 at the end, so then we have a plus 1 squared, right? So that equals what we just started with. And then I know that I'm not going to be able to take the Laplace inverse of this. However, if I write it this way, I can then write it like this. Oh, sorry. Oh, I need to write it like this. Okay, why am I writing it like that? Because now it's clear what this is equal to. If we use our Laplace table, we could see that the one on the left is going to be cosine and the one on the right is going to be sine. Okay, however, it's not quite right because we have to use the shifting theorems, right? We've shifted this over by 2 spaces, and so this is the first shifting theorem. So what is this equal to then? This is equal to the Laplace of e to the 2t. So this is going to be e to the 2t and then cosine of 2t. Oh no, cosine of t, I'm sorry. Yeah. Right? It's cosine of t because of the plus 1 squared. So it's e to the 2t cosine of t, and then minus 2, and then e to the 2t again for the shift, and then sine of t. Okay, So let's remember what the problem asked us for, okay? This entire thing then is equal to the Laplace inverse of e to the negative 3s times the Laplace of e to the 2t cosine t minus 2 e to the 2t sine t. So what does this mean? Or I should say, what is this equal to? So now I'm going to apply the second shifting theorem to this. Remember, the way you apply this is you replace every t inside with t minus the shift. In this case, the shift is negative 3. That means I'm going to replace every t inside with, sorry, I said that wrong. The shift is 3, right? Because remember, it's always negative as. So this means I'm going to replace every t inside with t minus 3. And then this is going to equal oh yeah, and I need the unit function, right? So it's going to be u3 of t, and then I have e to the 2 t minus 3 cosine of t minus 3 minus 2 e to the 2 t minus 3 sine t minus 3. So this would be our Laplace inverse. This is the answer. See, it could be really tricky to apply the theorem in both ways, but remember, you do not have to memorize these formulas. Okay, the formulas are there on the Laplace table, but you need to practice going back and forth both ways. Okay, so now comes the part where we actually get to use this to solve some differential equations, okay? So this will be our first example. So let's use this knowledge to solve some initial value problems, okay? Now this is going to be a lot trickier just because the algebra gets really cumbersome. The first problem won't be that bad. However, the second problem is going to be a lot of work, okay? But let's go ahead. So our first example, we want to solve the initial value problem. This initial value problem is y prime minus y is equal to 1 minus t minus 1 u1 of t, and y of 0 is equal to 0. You'll notice that because of the unit step function in this problem, we had no way of solving this problem before. We actually couldn't have even used an alternate method, even if we wanted to. So we're going to start by applying the Laplace transform to this entire thing, okay? So if we apply the Laplace transform of this entire thing, first we have to take the Laplace of y prime. Now remember, we already had we already figured out how to take the Laplace of a derivative. So this is going to be, so when we take the Laplace of this guy, we're going to end up with s y of s minus y of 0. So I'm just underlining where that came from. And then minus y of s, again, this became that after I took the Laplace. And this is equal to what? So what's the Laplace of 1? We know that the Laplace of 1 is 1 over s minus, and now remember, this is u1 of t times t minus 1, And so I'm going to apply the shifting theorem to this, right? This is the second shifting theorem in action. So the shift is a 1, right? Because that's the number that matches for both of those. So it's going to be e to the negative s, and then what goes there is the Laplace of t, which is 1 over s squared, right? So it's going to look like this. And again, this is the Laplace of t. Why t? Because it was a t minus 1 before, and now it just got shifted over, right? Okay, so now what? Now we need to isolate y of s. But remember, we can plug in the initial conditions first. We know that y of 0 is 0, so this is just 0. So that's not going to matter, right? And so what we end up with, if we factor out a y of s, we get an s minus 1 on the left side. And on the right side, we end up with 1 over s minus e to the negative s times 1 over s squared. And then if we divide both sides by s minus 1, this means that y of s is equal to 1 over s times s minus 1 minus e to the negative s times 1 over s squared times s minus 1. Okay? Now, this is going to be tricky because we actually need, we know we can't take the Laplace inverse of this until we use partial fraction decomposition. And actually, we're going to have to use partial fractions on this and on this. Okay, you can tell that's going to be a lot of work, but it's not really that bad. Okay, I'm going to work it out on the next page here. So here's going to be our partial fraction decomposition. So let's begin with the first guy. Remember, we had 1 over s times s minus 1. And I'm going to start by writing this as a1 over s plus b1 over s minus 1. And this gives me that 1 is equal to a1 times s minus 1 plus b1 times s. If I plug in s equals 1, this just gives me that b1 is 1. If I plug in s equals 0, this gives me that a is negative 1. Okay, so we're done with our first partial fraction decomposition, and let me go ahead and write down what that means, okay? This means that this is equal to, remember we got negative 1 first, so it was negative 1 over s plus 1 over s minus 1. So we got those two. And then I'm going to put this one down, e to the negative s times. Now I still have to do partial fraction decomposition on the second part, so let's do that now, okay? This one, notice that we have a negative 1 in there, okay? So how would I write that down? I have a negative 1 over s squared s minus 1. This is going to equal a2 over s plus b2 over s squared plus c2 over s minus 1. This is why I use subscripts, because I knew I was going to do partial fractions twice. Okay, so what does this imply? So this implies that negative 1 is equal to a2 times s minus 1 plus b2 times s minus 1 plus c2 times s squared. So if I plug in s equals 1, this implies that c2 is negative 1. If I plug in s equals 0, this implies that b2 is positive 1. And then if I use the quadratic term, I can actually solve for a2, right? So this means that 0 is equal to, what do we get for a2? it would be a2 minus 1, right? Because, again, I'm looking at the quadratic coefficients, and it's those two, right? And I already know that c2 is negative 1. So what does that give me for a2? This implies that a2 is also 1. So now that we've got our partial fraction decomposition finished, remember, each of these corresponds to the numerators of this, this, and this, right? So going back, here's what I can write this as. This is equal to, so I have a 1 over s plus a 1 over s squared, and then a minus a 1 over s minus 1. We're about to apply the shifting theorem here, okay? So it helps to rewrite these as Laplace of something, as we've been doing before, right? So this is equal to negative 1 over s plus 1 over s minus 1 plus e to the negative s times. So first, 1 over s. 1 over s is just the Laplace of 1. What about 1 over s squared? That's the Laplace of t, right? And then 1 over s minus 1, but I have a minus there. That's going to be the Laplace of e to the t. Again, all of these you can find by looking in your formula sheet, right? Okay, so we're now ready to write down the answer. So we're finally ready to write the answer now. I'm going to put this on the next page just because I'm running out of space here. But the point is that when we use the shifting theorem on this right part, you're actually going to replace all of the t's that you see here with t minus 1, right? Because that's the shift. That's the shift that we're getting from this, right? And so the formula or the answer becomes, so we're going to take the Laplace inverse. Maybe I can write it on the same page here just so we can look at it as we go, right? So then this means that y of t is going to equal, what's the Laplace inverse? We're going to go one term at a time. What's the Laplace inverse of negative 1 over s? So this is going to be negative 1. And then plus the Laplace inverse of 1 over s minus 1, e to the t. And then what about this next part? Again, use the shifting theorem. This is going to become the unit step function. It's going to be u sub 1 of t times, what does this become? It becomes 1 plus, remember, every t is going to be replaced with t minus 1. So it's going to be 1 plus t minus 1 minus e to the t minus 1. So again, what I'm doing is I'm taking this t is going to become a t minus 1, and this t is going to become a t minus 1. But what's 1 plus t minus 1? These cancel each other out. And so our answer is y of t is equal to negative 1 plus e to the t plus u1 of t times t minus e to the t minus 1. We just solved the initial value problem. A lot of stuff going on, right? Because we used the shifting theorem, and I believe we used both shifting theorems, right? At the very least, we used the second shifting theorem, and we used it a couple of times, right? We used it at the beginning to take the derivative of the Laplace of this original unit step function, and then we used it at the end again. All right, we're going to do another problem now. This one's going to be even harder. I'm going to do the partial fraction decomposition part quicker, just because I don't want to spend too much time on one example. I don't want the video to be boring for you guys, but I'm going to solve the following IVP. This one will be more complicated because it is a second order, okay? So it's going to be y double prime plus 2y prime plus 5y is equal to f of t, and y of 0 is equal to 0, y prime of 0 is equal to 0, and I have to tell you what f of t is, okay? F of t is actually a piecewise function. It's 10 if t is between 0 and 4, negative 10, t is between 4 and 8, and 0 when t is bigger than or equal to 8. So it is a piecewise function, but remember we have practiced writing this in terms of unit step functions. So what about this guy first? Well, remember we start with 10 being turned on, and then we're turning it off at 4. All of that is times 10, right? Next, for this guy, we're turning it on at 4, and we're turning it off at 8, and what we have left is negative 10. And then for this guy, well, think of it this way. We're not really turning anything on, or you could look at it as we're turning on at 8 the function 0, but that's not going to contribute anything. You don't have to worry about it because we've already turned off the one above from the step above, okay? And so we're ready to write down our initial value problem. Our IVP actually is y double prime plus 2y prime plus 5y is equal to, I'm going to combine all that stuff. It looks like this, okay? I actually have 10 minus 20 u4 of t. Where am I getting this from? I'm just starting off by distributing the 10 here, and then I have 20 of them because I have minus 10 of them from the next one, right? So that is where I get my minus 20. And then I have a plus 10 u8, right? So it looks like this. Okay? So this is where I am right now. And now I'm going to take the Laplace of this, okay? So applying the Laplace transform. What do we get? So how do you take the Laplace of y double prime? Remember we actually have our sheet that reminds us of how to do that. We end up with s squared y of s minus s y of 0 minus y prime of 0. So this was what our sheet said, right? This is what our sheet says for how you take the Laplace of a second derivative. So that's what I just did. Okay? And so let's keep going here. What is the next part going to be? So all of this, by the way, was just taking the Laplace of that first guy. Now we have plus 2 times the Laplace of the derivative. What's the Laplace of a derivative? Remember, we have a formula for that as well. It's going to be 2sy of s minus 2y of 0. I have a 2 twice because, again, I'm distributing the 2. And then plus 5y of s. So just to let you know where these things are coming from, that guy turned into this, and this guy turned into that. What's this going to equal? Well, we should know how to take the Laplace of the right side. First, I have 10 over s, right? Because 10 times 1, and the Laplace of 1 is 1 over s, right? What about the next one? I just have the unit step function there, right? So how do you take the Laplace of the unit step function? Remember, that's going to be the shift. It's going to be e to the negative 4s. And then I'm doing the Laplace of 1 again, which is just 1 over s. So it's going to be minus 20 e to the negative 4s over s. And then the next one's going to be plus 10 over s e to the negative 8s. Okay? Now what? Let's use our initial conditions, right? We have here that y of 0 is 0 and y prime of 0 is 0. This is good. That means this is 0, this is 0, and this is 0. Okay? So what's left? This means that I have y of s times, if I factor it out, I get s squared plus 2s plus 5. All of that is equal to, I have 10 over s minus 20 over s e to the negative 4s plus 10 over s e to the negative 8s. So I can now divide the entire thing by s squared plus 2s plus 5, and so I end up with the following. I end up with y of s is equal to 10 over s times s squared plus 2s plus 5 minus e to the negative 4s times 20 over s times s squared plus 2s plus 5, and then plus e to the negative 8s times 10 over s times s squared plus 2s plus 5. Okay, you can see that we are seeing a lot of repetition here, okay? And what I want to actually do here is recognize that because we have the same fraction appearing 3 times, we do need to use partial fraction decomposition here. However, we're only going to need to do it once, okay? So this is what I'm going to do to make my life a little easier. I'm going to pull out a 2 here. So if I pull out a minus 2 here, then this becomes a 10 just like the others. And so this is going to allow me to do my partial fraction decomposition once, right? Okay, let's do this on the next page. So what is the partial fraction decomposition? I actually want to figure out what 10 over s times s squared plus 2s plus 5 is. So understand first that this is going to become a over s plus, and then it's going to be bs plus c over s squared plus 2s plus 5. Okay, now I don't want to go through the entire partial fraction stuff. I just want to tell you guys what the answer is, okay? So what you end up finding out is that a is 2, b is negative 2, and c is negative 4. Okay? All right, so what this means, if we go back, it means the following. It means that we have 2 over s plus, and then this becomes this. Now, I'm going to keep going actually on this page. This is sort of like my scratch work, right? The reason I'm going to keep going is I want to make sure that we write this in sort of Laplace-friendly form, right? I want to make sure that we figure this out correctly. Oh, sorry, I wrote this wrong. This should be a minus 2 minus 4, right? There we go. We're going to keep going and then write it in Laplace-friendly form. Okay, so how do I do that? Well, I'm going to first write this as 2 over s, and then I'm going to pull out a minus 2, and then this is equal to s minus 2 over s. Now, before I write this down, this guy, if I do completing the square and I want to write it as the sum or difference of 2 squares, I actually get the following. This is s plus 1 squared, and that gives me that middle term. But then I have a plus 1, and that's plus 4. That works out. So I can actually write this as s plus 1 squared plus 2 squared, right? S plus 1 squared plus 2 squared. Okay. Oh, I noticed another mistake, that if I factor out a negative 2, actually, this top should be a plus. So sorry about that. There we go. So this is correct right now. And so what I'm now going to do is I'm going to write s plus 2 as s plus 1 over that and then what do I have left? I took out an s plus 1, so I still have a 1 there. Okay, so I'll write it like this. Okay. This is also equal to if I distribute the 2 now, I actually do want the 2 to be in there. The reason that I want the 2 to be in there is so that I can apply the sine and cosine formulas, okay? So I'm going to go ahead and write these as the Laplace of stuff, right? So what is this the Laplace of? So this is equal to the Laplace of, so first, the Laplace of what gives you 2 over s? This is going to be the Laplace of 2. Okay, so the Laplace of 2. Next, I have a minus 2, and now I'm going to apply the first shifting theorem, right? This has been shifted over by 1, so this is going to be e to the negative t. And then I know if I look at my formula table, this is going to be a cosine. What is it going to be? Cosine of 2t. So it's going to look like this. Cosine of 2t. And now for this last one, I have the same shift. So I'm going to write e to the negative t, except now I have sine of 2t. You'll notice that this guy does not have the 2 there, right? Because the 2 actually got absorbed into the formula, right? The formula is b over s squared plus b squared. Okay. Okay, this may be confusing, right? But what I have done is I have taken that common thing that appears in all of these, and I wrote it as the Laplace of this thing. So let's go back to our original problem. Remember, this is where we were, except now I know that y of s is equal to, look, all of these guys are the same. All of these guys are the same. So I'm going to write it this way. The Laplace of, let's write it correctly, we've got 2 minus 2e to the negative t cosine 2t, and then minus e to the negative t sine 2t. That's the first guy. And then we have minus 2 e to the negative 4s times the Laplace of all that stuff again. And then plus e to the negative 8s times the Laplace of that same stuff again. So then, what would y of t equal? Remember, I need to figure out what the Laplace inverse is of y, right? So what is the Laplace inverse of all of that stuff I just wrote down? Well, the Laplace inverse just undoes the first guy, so I'm going to write this as 2 minus 2e to the negative t cosine 2t minus e to the negative t sine of 2t. Let me erase this here. I'll specify later what I'm doing, right? And now, how do I apply the Laplace inverse to this next part? I need to use the second shifting theorem again because I've got this e to the negative 4s being multiplied by it. I know that's going to become the unit step function at 4. So it's going to be minus 2 unit step function of 4 of t. And then what am I going to have in there? I'm going to have all that stuff except instead of a t, every t that I see, I'm going to replace it with t minus 4. So it's going to be 2 minus 2 e to the negative t minus 4 cosine of, if you replace t with t minus 4, that's 2t minus 8 minus e to the negative t minus 4 sine of 2t minus 8. So now I have to do it one more time because this time I'm shifting this way. I'm shifting 8 spaces. So this is going to be plus u8 of t. And then what's left? Now every t I see, I have to replace it with t minus 8. Okay, so remember, all of this that we wrote down is y, and all of this is Laplace inverse of y, right? So this is us taking the Laplace inverse, and of course, we did use the second shifting theorem to be able to do this. Yes, it's a pretty crazy problem, but these problems do involve quite a lot of algebra. You may be wondering if there is an easier way to do this, and not that I know of. We have no other way of dealing with piecewise functions. So when you see a piecewise function, just keep in mind that Laplace is really the most efficient and best way of dealing with this. We just have to learn how to use the shifting theorems. Okay guys, thank you so much for watching. I hope that was clear.